Hey guys, Mr. B here, and in this video we're going to be going over speed and velocity in chapter 11.2. So let's get started. What is speed? Now most of you guys probably know what the word speed means. We use it pretty commonly in our everyday language, but we're going to go over what it is in physics and science. So speed is the ratio, which is a fraction of the distance an object moves to the amount of time the object moves. So it's basically distance over time. Okay. Now the SI unit for speed, which is the International System of Units, this is the science unit of speed, is meters per second. The unit that, of course, we are familiar with in the United States is miles per hour, or maybe feet per second, you know, if you're looking at maybe speeds of bullets or something else. But miles per hour and feet per second are the most common ones here in the U.S. However, because we do not use the metric system in the U.S. and we do in science, we're going to be using meters per second, okay? Now, two ways to express speed of an object is either as average speed or instantaneous speed. So we're going to go into what each of those are. Now, average speed is going to be computed for an entire duration of a trip, okay? So an average speed is going to be, as it sounds, an average, which you can get in one of two ways, okay? One, you could add up all your speeds throughout your trip. If for some reason you were to be calculating your speed at different portions of a trip, you could add them all together and then divide by however many you added, right? Like you'd get for any other average. Or, and we'll look at the equation for this in a second, but you could take the total distance of the whole trip divided by total time. That would also give you an average. But either way, an average speed is going to be a speed over a long period of time with speed changes. So there might be times you're going faster or slower, and average is just smooths it all out, right? Whereas instantaneous speed is at a particular moment. So we'll get into some examples of what that one means, though, in a second here. So average speed is useful to know how fast something moves for an entire trip, or maybe how fast something moves for a longer duration of time. For example, like if you're a track runner or a football player, or any athlete, I guess I should say, even soccer players, you might have a time for your 40-meter dash, right? Or something like that, where, they time you and you run. That speed, if you were to take 40 meters divided by your time and get your speed, that would be an average speed, okay? That is, on average, how fast you're running over 40 meters. But there are times during that 40-meter dash where you're running where you're going faster or slower than maybe you started, right? So, like, you start slow and you speed up until eventually you hit probably like a max speed. But then you might get tired. You might slow down a little bit before you get to the end. And so all of those little bitty moments are different changes in speed. But on average, right, we would average it out. So we take our total distance divided by our total time. Total distance is, it's like, why? That looks funky. There we go. Total distance is usually going to be in meters, or it could be in miles if we're not doing metric system, or kilometers. Total time is usually going to be in seconds, though I guess we could do it in minutes or hours, okay? But either way, total distance divided by total time. As for instantaneous speed, I'm going to skip past these practice questions here. So as for instantaneous speed, again, this is a particular moment in time. So the best example I can give you here is a speedometer, like on a car, right? When you're in your car and you want to know how fast am I going right now, you just look at your speedometer and it tells you, right? Right at that moment. But 2 seconds later, you could be going slower or faster if you let go of the gas or you push it down harder, right? And, 10 seconds after that, you could be going even faster or even slower, or the same speed. And it's constantly changing. So instantaneous speed is like right now in this one moment, and 2 seconds later, it could be something different. So instantaneous speed is more useful when you're trying to track something in particular. So, let's say, for example, you're a cop and you're trying to, use your little radar gun to clock people's speeds and see if they're speeding. That's instantaneous speed. So you want to know how fast they're going right now. And, if it's over the speed limit, I'm going to pull you over. So the equation is the same for both average speed and instantaneous speed. It's just that average speed is like a long distance divided by a long amount of time, and instantaneous speed is usually a shorter distance over a short amount of time, because it's only for a moment in time, so the numbers are usually smaller. But anyway, okay, so moving on. let's talk about graphing motion. Okay, so understand that speed can, be average or instantaneous, but we also want to understand how motion can be visualized, okay? Because this is going to lead us into velocity. So we're going to talk about motion graphs, or distance versus time graphs. And now distance we learned about in the previous section. Distance, of course, is just how far something moves. There's no direction component to it. And time, of course, we all know what time is, but use that to, determine how long it takes for something to do something. And so with these distance versus time graphs, what we do is we graph distance on usually the y-axis and time along the x-axis, and we can get a visual about how something is changing its speed over time. Okay, and we can use the slope of the graph, it's usually a line graph, to determine its speed. So this is a really, really useful thing because distance versus time graphs can give you a lot of information about the motion of an object without having to say anything, right? You literally just look at it and you go, oh, and it can give you all this information. So it's a lot faster to relay information. Okay, so here's an example of a distance versus time graph. We have 3 different ones, and each is a different object moving at a different kind of way. And I'll kind of explain what each graph is. So the first line we have here is just the green, straight, increasing line. This would be a fast, steady speed. Okay, it's fast because the slope is steep. So the steeper the slope, the faster the object's traveling. And it's a steady speed, meaning it's not speeding up and it's not slowing down. It's going at a constant rate because that line is straight. Okay. The blue graph here is showing an object that is accelerating, that's speeding up. So as time goes on, the graph is getting more and more steep because the object is increasing its speed, or it's traveling a further distance. So it starts off like this, but then as it accelerates, the graph starts to curve upwards more. So this shows acceleration, okay, this blue line does, whereas the green one shows something just going at a constant rate and it's not speeding up or slowing down. And the red one here shows an object kind of changing up its speed. So the first part shows the object moving at a set speed, not super fast because the slope is less than the green one, but it's not accelerating. Then you hit this flat part, okay? This flat part shows that the object is not moving anymore. And we know that because we can see that the distance portion of it is not increasing or decreasing. So it's sitting at the same distance the whole time, but time is still going on. So it's just standing in place. And then this last part here, this downward part of the graph where it goes down, is actually showing that the object turned around and is going back towards where it started. Okay, it's not slowing down. And we know this because imagine that where these graphs are starting, that's like your starting point. And as the distance increases, that shows that you're moving away from your starting point. But if the distance decreases, as it's shown in this red part of the graph, that means that you're now getting closer to your starting point because the distance from where you are and where you started is now decreasing, meaning that you've turned around, you started walking back towards that spot. So this red graph would show an object moving away, stopping and standing in place for a bit, and then turning around and going back towards where it started. Okay? All right, and there's some more practice that we'll be doing on that in some other videos. So if you need more help on that, go watch those ones or talk to me. So there, of course, is going to be a video of me going over these practice problems. You can watch that on your own time, but let's just finish up the last bit of information. And the last section here then is velocity. So we've talked about speed, which is, of course, just how fast something travels, and it's usually a distance divided by a time. So how is velocity different? Well, it's actually very similar to the difference between distance and displacement. Speed is just how fast something travels, and velocity is how fast it travels and what direction it goes in. So basically, the only difference between velocity and speed is that velocity includes that direction component. Speed does not, which means that velocity is a vector, just like displacement was a vector. So when we draw velocity, we can draw it as an arrow, and that means also that all of the math that we can do with displacement and vector addition, which was in the last section of notes, we can also do with velocity vectors. Okay, so vectors of varying length can be used to describe motion of an object. A longer vector would represent a faster velocity or a faster speed. A shorter vector would represent a slower speed or a slower velocity. Okay, and because, of course, change in velocity is a measure of speed and direction. If you change your speed, you are changing your velocity. If you change your direction, you just simply turn, you're changing your velocity. If you change both, right, you slow down or speed up and you're turning, you're also changing velocity. So understand that that direction component is a portion of velocity. And that's basically the only difference that makes it different from speed, is that it has direction. So it's a little bit more detailed, basically. It's more descriptive, which is helpful because, of course, when we're trying to talk about motion, being as descriptive as we can is always going to be helpful. So, all right, now, last little section is just about adding velocities, and it's super short. So basically, this is just saying, hey, we can do the same vector addition that we did with displacements in the previous section of the chapter. So if we have two velocities that are both pointing in the same direction, we can simply add them together to get a larger velocity vector. If we have two velocities that are pointing in opposite directions, we can subtract them from each other, and we can get a shorter velocity vector. Or if we have two velocity vectors that are at right angles to each other, right? So one's going sideways and one's going vertically, we can do the Pythagorean theorem and we can find the resultant velocity that way, which is basically the diagonal. Okay, we can do a squared plus b squared equals c, and then, or c squared and then square root that, and you'll get your velocity. And then, of course, you have that direction you got to add on there. So, all right, so that is it for this section notes, guys. Not super, super long. Again, if you have any questions or need extra help, make sure you reach out to me. The distance versus time graphs are a little bit tricky. Go watch the video of the practice problems and you'll get some help on it there. But otherwise, if not, there is more additional practice on Schoology in the resources folder. There's some videos going over distance versus time graphs. So, all right, guys, I'm Mr. B. Thanks for watching. See you in the next one. Bye.